Thanks, everybody. I'm happy to be talking to you all, and I appreciate the organizing committee for asking me to present to you guys. And so, you all have been hearing a lot about all the different data, the way that you can get at this data, and the thing that I'm going to talk about today is planetary geologic mapping. We're going to talk a little bit about the how, the why, and the when. So, just to give you a short introduction, Jim Skinner. I work at USGS in Flagstaff, Arizona. And we are in charge of creating what we call standardized geologic maps for planetary bodies. And so USGS, along with other geological surveys in multiple countries around the world, excel in creating geologic maps for the Earth. And so USGS in Flagstaff, since the Apollo era, has been creating these same geologic maps for places off the Earth. And so we'll talk about like how we do that, why we do that, and how we can use all the different techniques and data that you've been hearing about today to create these products. So one of the first things I like to talk about is this great quote. And so it says, most of the great battles are fought between the creases of geologic maps. And what does that mean? It basically is saying that, we can make observations, bold observations, but really the outcomes of any kind of endeavor often hinge on the small details of geography and terrain. And so basically larger, we kind of zoom out a little bit, is that human endeavors in general depend not on just the larger, most obvious factors, but a deep understanding of the environment that we sit in. In this case, the creases are metaphors, of course, and they mean the overlooked details that can often change the direction of an effort. And so I like this quote because it talks about how geologic maps can really be used to solve some of the problems that we might not even know exist. I think it's important to point out, especially for you guys, is that we are in the middle of a geologic mapping renaissance. We have many things that are going on to all of our disposal, which is basically a fleet of exploratory spacecraft. We have a whole fleet of things that are all through the solar system that are gathering all kinds of data. And so that lots of data for many different bodies, lots of different kinds of data, lots of spatial resolutions of that data. And taking that data alone doesn't do anything for us. We need to be able to get it to a place where we can actually analyze that data. And so the easiest, quickest thing is a GIS. And so these advanced analytical capabilities that allow us to overlay data on top of each other, but not just that, it's also analyze them all together. And so one of the last things that we have is, of course, we're studying all the different bodies that we have data for, but one of the things that are most pressing is that we as a community, we as the US, we as the world in general is preparing for a sustained lunar presence. We are all serious about getting back to the moon, and that's the next step from the moon onto Mars. And so geologic mapping, we say this all the time, is that you would never go anywhere in the field on Earth without a map and a geologic map. You would never take 1 foot step on any other body, especially the moon, without having a geologic map. So geologic maps are going to be critical to exploration. They provide context, and we're going to get into some of the details of that today. So let's start with some of the definitions and methods that we talk about here. So not to insult anybody's intelligence here, but a geologic map is like, what does that really even mean? A geologic map is basically just a chart or a map that displays bulk geologic observations. And I've underlined observations there because it's really important that we get a handle on what observations are versus interpretations. And we'll get to that a little bit later on. These charts are intended to visualize and convey the formative history of any one particular area. It essentially is establishing some kind of context for which we can operate, whether that operation is scientific endeavors and investigations, or it is roving across the surface as a human or as a vehicle. On the left-hand side here, we have the San Francisco volcanic field, which is a volcanic field that's north of Flagstaff, Arizona. On the left-hand side, you see the image that's coming remotely, satellite images. And on the right-hand side to that image is the derived geologic map. And so geology and geologic maps have been around for a very long time. And essentially, when we really boil it down, is that we like to think of geology as the anatomy of landscapes. It's basically telling the story about where things are, how they got there, and the way we can apply those to different bodies. So how do we do this? Well, on Earth, we do this through field observations, right? And so we go out into the field, we take samples, we identify what rock units we might have there and how those might vary from one place to another. We draw contacts, and so those contacts are basically showing the difference from one terrain on one side or one geologic unit that was in place one particular way. from an adjacent unit or terrain that was in place a different way. These can be sedimentary units, they can be metamorphic units. In this case, for this picture right here, they can be volcanic units. Often from remote data sets, those look very similar. So we can't always get the full picture without having access. One of the things that we strive to do when we're talking about planetary geologic mapping is getting the best inference for that. So it's important to note that field observations are the key to geologic inference on other bodies. So how do we map geology on other bodies? In this case, the picture is the moon. And that's why everybody is here today, is to talk about how we do these things. It's not just mapping the geology, but it's understanding what data exists, what does that tell us about these particular bodies, how different scales matter, whether we're mapping at the global scale for the moon, for example, or we're identifying landing sites for the Artemis missions. So all of these tie together, depends on how much we use the data, what data is relevant for one thing versus another. So how do we actually do this when we're doing it on other bodies? So this is just a screenshot of one of the ARC projects, so a GIS project that we're working with right now. This is looking straight down on the lunar South Pole, and the yellow boundary is an area that we're working on for some conceptual mapping that we'll talk about a little bit later on. This is important because this is how we do it for planetary mapping, is remote observations. So we don't have the ability to snap up to any one place that we might want to go explore and start taking samples. And so that's obviously very logistically challenging. We're not going to be doing that. What we do have is a bunch of data. And so that data depends on what body we're looking at. Mars and the moon have the most array of data that we have for any other body except for Earth. And so on the left-hand side here in that blue box, we're seeing all the different data sets that we have that are going to enable us to identify and characterize the geology, the terrains, the features of any one body. We have past geologic maps. For the moon, we have permanently shadowed regions, which are hazard areas. We have visibility with ranging between the Earth and the lunar surface, temperature, ice, mineralogy, roughness from radar, slope, elevation, visible imagery, so ortho images and ortho mosaics, and then derivative data sets like hillshades and slope roughness and that sort of thing. The point here is to show that there's a lot of information that we have to balance, and we can't go in the field and do those samples ourselves. And so we have to be very strategic on the data that we do use and how that is fit together, not just how they all go together in one scale, but looking at multiple scales, because we understand that a global map is going to be different than a landing site map. So I like this slide because it really starts to inform that terrestrial mapping versus planetary mapping. On the left-hand side, we have this kind of scale where field work is really the predominant thing that we do. We go out into the field, we might have to fly there if it's something that's logistically challenging, but we still get to have boots on the ground. So taking samples, we're doing mapping, we're looking at the orientation of any kind of stratigraphy in space. We might take some of those samples and go back to our home institution and do some lab work, send them away for lab work. But in the end, we really have access to the materials that we're trying to characterize. And so the field work, that direct observation, is vastly outweighing the orbital information that we're using from remote data sets. The flip side happens with planetary geologic mapping, that orbital data is definitely outweighing anything that we have from the field. And in fact, in many places for planetary geologic maps, we have no access whatsoever for the field. We might have some kind of samples for the moon that were brought back by Apollo, for example, and we can try to correlate those, but we're studying in different areas. So there's not much that we can do other than rely on the orbital images, rely on those remote-based images. And so we have diverse data. Under planetary geologic mapping, you have the DTMs and composition. On the right-hand side, this is a crew of astronauts that are walking down into Meteor Crater here in northern Arizona. An analog expertise, analog meaning what is an equivalent type of terrain on the Earth that we can access, that we can learn from, and then apply that to planetary geologic mapping. So it's really, really critical that we have access to these terrains, that we understand what those geologic processes are on Earth, so that we can apply them to other bodies. So I hate to say it, people don't like to hear this, but we do not know what the geology is on any given body. Okay, we infer, so we know the processes and products on Earth, We've gone out there, we know what different terrains are. So for example, if we have a meteor that's bombarding on Earth, it will form an impact crater depending on the certain size of the incoming bolide. And we can study that. We understand that impact craters are on every other body in the solar system in some form. And so that gives us some place to look, some place to compare. On the right-hand side, we have basaltic volcanism, something that's happening within crust, this material coming up straight from the mantle that will form a certain kind of rock. In this case, we're talking about a basalt. And so we know the processes on Earth, we know the products on Earth, and so we can form what we're calling a well-reasoned inference. That is basically saying that we understand these things on one body, we can apply it to another body within reason and within those boundaries. Again, this brings up analogs, and getting in the field is really, really important as a geologist so that we understand what we're seeing and we can apply it to different bodies. Here's a little cutaway of kind of a schematic cartoon of the lunar near side. This is from a paper that was published by Don Wilhelms from the USGS 40 years ago or so. And love this cutaway. You might see it in other presentations, but it really shows kind of these 3D depictions of what we're seeing on the lunar surface. We see this straight up when we go out in the field. We can see these layers, we can see the stratigraphy, we can see the materials. On other bodies, we have to infer this. So there's that well-reasoned inference. The numbers here are indicating age, one being the oldest. Those kind of mountains that are poking up from the background of horizontal plains are the oldest, and they're projecting that into the subsurface. 2 is the flooding deposits, 3 is ejecta. And so you have this sequence from 1 being the oldest to 5 being the youngest. And our job as geologists, our job as scientists is to help unravel that, is to start peeling back all these different layers so we can get an understanding about what units are there, how they were in place, how they might differ from what we understand on Earth, and how we can apply that to other bodies. And so geologic maps are the key that document all this and try to convey it to ourselves, to our colleagues, as well as to the general public. I love this quote. This is Don Wilhelms and Macaulay in this 1971 USGS map of the lunar near side. And this is kind of dumbed down a little bit, but it says the goal is to portray units that are not just similarly appearing surfaces, but three-dimensional bodies of finite horizontal and vertical extent. These are, in effect, the building blocks of the crust. So it's really important, I think, to step back and think about, are we just circling things that are knobby or things that are smooth? And that's often what we're doing, but we go one step beyond and we're trying to infer that something that is knobby or smooth is a part of a three-dimensional piece of rock or sediment. And so our job as geologists is to identify that unit and then project it both vertically into depth, meaning time, and also try to infer what it means in space. And so these are the building blocks of the crust. This is what we're trying to get at with geologic mapping. So let's talk a little bit about standards and map components. For USGS maps, we talk about standards, meaning that we have a certain set of rules that we will publish terrestrial and planetary geologic maps. This doesn't mean that everybody has to do it this way. That means that these are the rules for all products. They certainly can be used by other folks, but they should also be adapted because our rules are for one certain kind of product. It just establishes that the products that we create can be viewed and compared consistently with other products. It doesn't mean that's the only way to do it, and we should certainly think about that. So in this case, we're not going to harp on standards very much. We're going to kind of review them and talk about them. The most standards that we will talk about are map components. When we see a giant map sheet, which you all might have access to or might have one hanging on your wall, whether it's from the USGS as a planetary map or from your geological survey, maybe from your own country, there are certain pieces of those maps that are almost common across the board. So in general, the map itself, circled here or boxed out here in that blue box, is that the map is the key part of the geologic map, but it's not the only part. The map itself is showing units. Those are the different kind of discrete terrains and pieces of rocks and sediments that have been replaced by certain processes, and then the contexts that separate those together. Often these are colored. Colors can often mean that they have different kinds of formational mechanisms. And this one map from Ken Tanaka and others from the USGS for Mars, the browns are really the older, kind of higher standing terrains. Yellows all over the place are the impact craters that sit on top of that. Greens and blues tend to be sediments that have eroded and transported across and been deposited in different areas. And then reds are volcanics and anything that might have come from the subsurface and spread out over the surface. So we have units and contacts, we have colors. One key thing that it seems to be kind of in the weeds, so we always classify this as boring but important, right, is the projection that we're using. In this case, we're using a Robinson projection. It's trying to depict a spherical surface, whole body, onto a flat map. And so that gets into projections. Every projection has its own kind of issue with scaling and errors. And so we try to find the best way to project this information. In this case, we're using a Robinson projection. The scale is also important for the geologic map. The scale here is 1 to 20 million, meaning that one unit on the map equals 20 million of those units. So if we're talking about millimeters, 1 millimeter equals 20 million millimeters, which equals about 20 kilometers. So 1 millimeter on the map equals 20 kilometers on the ground. The scale is key. So moving on to the next component, the correlation of map units, or what we call the COMU. You can see this boxed out right above the geologic map. This matches the map in color. And so every color that is represented on the geologic map is represented on the correlation of map units. And this is showing those relationships between the units. It's just another way of depicting how these units sit in space and time. Often you will see that these little boxes that represent the geologic units may be stretched vertically or even horizontally. This says something about how those units or when those units were deposited. The ones on the bottom were deposited further back in time. The ones on the top were deposited more recently. So we're trying to get a handle on like how these units fit together in space and in time. Also included on these correlation map units, depending on what body it's on, are major events. Things like the development of the farthest volcanoes on Mars. When did that happen and how did that affect all the different surrounding units? Giant impact basins like Hellas or Argyre or Utopia, when did those happen and how did that affect the subsequent geologic processes, the subsequent units? And so all of these things go into the correlation of map units. Often you can take that without the map at all and start to interpret how geologic units were placed on any particular body. It's a very powerful tool. And it's important to note, every planetary body has its own different way of representing this correlation of map units, as do terrestrial geologic maps will also vary. And so you have to have some expertise or understanding about how these units are being represented in the correlation of map units. But a very powerful tool that complements and often can stand alone against the geologic map. The next key component of a geologic map is description of map units, or the DOMU, highlighted here on the right-hand side in the blue box. So these are the objective descriptions of any one unit. Those key characteristics, often grouped by the way it looks in a primary base map. We identify one or two base data sets that we will define and draw units on and start describing them. You'll also have a description of supplemental data sets. If you have a lot of data, as you do on Mars and the Moon, you will have a primary base map that you draw and define things on. To have supplemental information about how something looks. So these are the key characteristics using multiple data sets. It's really, really important to note that interpretations are an extension of the description. They're not the same thing, and it's very easy for us to be able to separate those things out. For example, when we're mapping on the Earth, we might be able to say when we walk up to an outcrop that this is a basalt. It is composed of these certain minerals. We know how it formed. Or this is a sandstone of a certain grain size. Those are observations when we are mapping on Earth. Those are interpretations when we are mapping on other bodies, simply because we do not have access to those points. And so we cannot say for surety that those are sandstones or those are basalt. So this is one of the key differences between planetary maps and terrestrial maps, is that we are very specifically separating out description from interpretation. They are not the same thing. We should always be very careful with our own work, and also when we are reading and reviewing other work is that to make sure that these things are separate. A description for a unit on Mars at this scale might be something that says, you know, bumpy at the kilometer scale, underlies a volcanic unit and overlies some crater unit. And then we can say something about the interpretation is a sedimentary unit that was deposited by outflow channels. And so those two things are very separate, and it's important to keep them that way. One thing that's not a typical component, but is very powerful, is adding in different figures. And so here's one that's boxed down below the map. And so this is basically showing the locations of our crater counts, the locations of the highland-lowland boundary, any kind of ancillary information that we want to present are being included in figures. They can provide extra explanation. They can also be extremely, extremely useful, particularly if you're this guy who has that figure on his desk. So just a fun little point in there. The last point here is the map text. And so the map text is often on the map sheet itself, or in this case, it comes as a separate pamphlet. That includes the background, all the different geologic mapping that has been done or topical studies that have been done in one particular area. A rationale is like, if you have, especially for Mars, this is a great example, is that this is the third global geologic map of Mars, one by Mariner data, one by Viking data, one by post-Viking data. And so a rationale would explain, why do we need another geologic map of one particular body? Just because you have new data doesn't always mean that you need a new geologic map. And so the map text will include the background, the material that's been done before this, the rationale, why are we doing this, the methods is like, how do we do this, what data do we use, what scales were we mapping out, a unit summary that complements the geologic unit descriptions that are on the map sheet. Features, if you're starting to map out features, are different than units. They're often associated, obviously, but they can be different. Normal faults or lineaments or any kind of structure like that. And then obviously the history is pulling everything together and describing from oldest to youngest how everything was put together based on the mapping, how we understand this, what were the processes, what were the units. So map text is key. So in general, the four major components of one geologic map is not just the map itself, but it's the map, correlation of map units, description of map units, the text, and then also figures might accompany that. So you say, Skinner, that's great. I really appreciate that. That's all very neat. Maps are beautiful, but what's the exploration value of these products? Why are planetary geologic maps important? There's a couple different reasons that we can pull off right off the bat. The one that I like the most is talking about Apollo 17. So this is the only geologist that was ever on the lunar surface, was a geologist from the USGS here in Flagstaff. That's Jack Schmidt. And so this, on the left-hand side, we see a pre-mission geologic map. This was done based on remote data sets, obviously. It was informed slightly by the preceding Apollo missions, although they did not go to this area. They had a better understanding about the lunar surface, about what they were seeing, about how to map that out. And overlaid on top of that geologic map is the Apollo 17 traverse path. So right there in the middle is where they landed. There's some white lines and the arrows that show how they maneuvered across the surface. This is one of the J missions, meaning that it wasn't just walking across the surface and carrying all the tools. They actually had the lunar terrain rover. So they're able to go a very long way. And this is showing that the geologic map was critical to be able to identify where they thought they were going to go, where they actually did go, and how to contextualize the samples that they brought back. Additionally, it enables people to talk about the features that they're seeing. So Jack was a very verbose person, an excellent geologist, and one of the things that he was talking about as they were roving across the surface for one of the stations outlined in red there is that he said things like the blue-gray rock near the contact with the anorthositic gabbro does have some vesicles in it. So everything that he's saying there was geologic information that's being conveyed to the back row. And the back row needs to understand what they're saying, because that might be the only observation that they made. They couldn't take back all the samples that they wanted to. They couldn't do analysis on the fly. So the scientific backroom for Apollo was listening to this and was trying to triangulate those observations. And the way they did that was putting it onto a geologic map. It becomes critically important. So another thing that we like to talk about is the purpose and use. There's two different things. So far, planetary geologic mapping has mostly been for fundamental science. That means it's capturing geologic phenomena, describing that for us to better understand the processes that are happening on other bodies. So it's a guide to contextualize research, understanding natural phenomena, understanding our environment, understanding other bodies and how it might compare or contrast with what we understand here on Earth. So that's fundamental science or basic science. It's just our ability to put our place in the world and understand the things around us. An extension of that that you can't get to without fundamental or basic science is applied science. Geologic maps that are made for the terrestrial environment here on Earth are often made so that we understand where things are. So can we build a tunnel through this one mountain range? Can we put a landfill for our waste far enough away from a city, and is it stable, and is groundwater not going to move contaminants away? So applied science. In order to apply the science, we need to understand what is there. Once we understand what is there, we can start to do things like looking at resources, looking at hazards, looking at civil infrastructure and siting things. So it's really important to be able to understand the difference between these two things, fundamental science and applied science. We are just now getting to a place with planetary geologic maps that we're moving from fundamental science, just understanding the geologic phenomena, into applied science, where we are looking at resources, we're looking at hazards, we're doing site selections, and we're starting to have an understanding about what it would take to have a long-term sustained presence on the lunar surface and beyond. It's important to note that a sustained presence absolutely requires an understanding of the potential use of the geologic environment. We will not go somewhere and stay for very long if we cannot use the terrain and the environment around us. To stay somewhere means that we need to be able to use aggregates to push together into a berm for safety, protect the habitation unit from the oxygen units that might cause some damage to these structures. So it's really important to understand that we're moving from one kind of science into another kind of science, and that's a good thing, and we can emulate what we know about these processes and products on Earth. Talk about a sustained lunar presence. Geologic maps and site selections are really important. So these are the old kind of 13 Artemis sites that have been proposed. They have since been refined, but this is around the lunar South Pole. Earth is facing us, it's pointing towards us, and the lunar South Pole is an arrow right there in the middle. And so there are 13 different sites, and those sites were selected based on safety, meaning that which of these areas have line of sight to the Earth. But they also were selected for the science value that could be returned from them. Often safety of assets, including humans and the people and the things that would be placed on the surface, are going to trump everything else. And that's the important part. But we also want to know, wherever we go, what is the geology that we can return from that. So geologic maps are critical in those site selections. Geologic maps are also critical to flight operations. So for example, a crew map, book, and cuff. We have been conducting some analog activities in the volcanic field north of Flagstaff. They're being conducted at night. These are some of the suited astronaut subjects in the field. But just like in Apollo, the crew will have an actual map book. They're not quite there yet where they're going to have a fancy heads-up display or fancy kind of wrist screen or anything like that. And so they will truly have a hard copy map book that will lead them from one place to another. They will also have a cuff checklist, kind of like a little book that's strapped onto their cuff. And that will include very detailed explanations about the environment that they're walking around in. Geologic maps, as I mentioned before, are very important for the science background to understand where the crew is and what they're seeing so they can triangulate these geologic observations. Station identification. Any station that they are headed to will be pre-planned. That doesn't mean that if they see something that's interesting that they will not stop and observe that, but there will be pre-planned stations with a list of things that can be done at those stations, basically science return. And the only way that you can do that is by identifying the geologic units that exist there, the kinds of samples that you think would be getting back, is basically answering all the different scientific questions that we have. And then, as I mentioned before, geologic maps and surface development. Units and contacts will beget hazards, ice deposits, aggregates, regolith strength and bearing capacity, communication and other logistical scenarios, sample locations, and eventually land use. What do we use the land for? How do we share it responsibly? How do we maintain it so that we are not ruining an environment as we progress and explore? So that gets into the Artemis mission. That gets into how geologic maps are used for missions and completing that. And it's important to talk about mission training, is that all the astronauts that will be going to the lunar surface. On the left-hand side, we have the 2017 astronaut class. They were called the Turtles. On the right is the 2021 astronaut class. They were called the Flies. On the left, everybody who's circled there has already been up or is planned to go up to the International Space Station. The 2021 class on the right-hand side, some of these folks will actually be landing on the surface of the moon and operating there. So it's important for us to get to the place where we are training ourselves and understanding what the geologic maps are capable of doing, as well as training the folks that will be there. These folks are not geologists, they are medics and pilots and engineers. And so it's important for us to understand what their background is and how we can train them for geologic mapping. They go through classroom training, they go through field training. It's important for them to come together and understand these processes. Another thing that's really interesting is that we've come full circle. In 1964, they were doing geologic mapping in suited subjects with suited subjects in northern Arizona. We're doing that again today. So we have learned from the history of the past. We will continue to do this work, and geologic maps are critical to that. So just to finish up here, pass forward. Where do we go from here? In my opinion, the time is now. This is kind of the renaissance of geologic mapping. We understand that geologic maps provide basic and applied science projects. They improve science, they reduce risk. We need to really emphasize field work, that good planetary knowledge is based on good terrestrial knowledge. You can't do things on the planetary surface geologically without knowing where it comes from and how to apply it and how to interpret it on Earth. It's a great opportunity to bring together science and technical professionals. International collaboration is going to be absolutely key because no one country can or should be doing all of this alone. We should be integrating and collaborating. It's also important to say innovate, innovate, innovate. We are really in a place right now where we're trying to understand what it takes to make a geologic map useful for exploration. And we want to support humans to the moon, and that includes Artemis. To that end, the USGS is helping NASA with understanding what the geologic maps will be for Artemis 5 and beyond. So right now we've already had Artemis 1 fly. Artemis 2 will be around the moon and back, not landed. Artemis 3 will be the first time that we are setting foot back on the lunar surface since the Apollo missions. And so before we can get to a sustained presence, we really have to have an understanding about what kinds of maps are available to us, what kind of data needs to go in there, who needs them, so who are our stakeholders, flight operations and tasking, geologists, material scientists, and civil engineers, so who the stakeholders are, what kind of information they need, when they need it along the mission timeline. So LMAP is the lunar mapping program that is funded by NASA, and we're basically tasked with understanding conceptual map products that would provide both geologic science, but also a context for making decisions for the lunar surface. So we have a team together that has just started working. We're working over the course of a year and a half, creating these kinds of different scientific products. We're not going to be answering all the questions, but what we certainly will do is to open up and create a vector for the places that we want to go with creating geologic map products. We look forward to sharing this with everybody. We also look forward to getting feedback from everybody. If anybody's interested in this, and feel free to email me, and we're happy to loop people in as we go through this process. So in conclusion, the future of planetary geologic exploration needs geologic maps, and not only geologic maps, but it needs the scientists and the good explorers to make this happen. So that's you. So I encourage everybody to understand what geologic maps are, join the journey, let's map the future together, let's be pioneers of planetary exploration. And yeah, if you have any questions about any of the stuff, then please feel free to reach out to me. Always happy to communicate with folks, always happy to point people in the right direction as far as what geologic maps mean and what we can do. We don't have all the answers, but collectively, we work together, we can get those and have a sustained presence of the lunar surface and continue exploring. So thanks for that. Happy to take any questions.